Hello everyone. So in this session, we'll try to understand what are the principle of rotating machine. Actually, this is the fundamental of understanding the velocity diagram and the various fundamental and principal aspects of turbo machines. Different turbo machines. Turbo machine is like compressor, axial flow compressors, turbines, and all those things. So understanding all those things, we have to first understand the basic principle behind that. So first, we'll try to understand by making some diagrams. Let's say we have a turbo machine. Let's say we have the front view of the turbo machine like this. Okay, and the side view if I am making, so it can be. So I will draw it again. Side view can be taken as this. Okay, and this turbo machine will be mounted somewhere. Let's say we have a bearing. This bearing will be actually foot step bearing, which will be somewhere mounted, and this is the side view and this is the front view. Okay, and let's say it is rotating like this. Okay, so now let's try to understand the concept. So let's say whatever is the fluid which will enter to rotate it for doing whatever may be the reason. Okay, let's say there is a fluid which is entering like this at a specific angle. It is V1. So the different components of this fluid will be this and this. So this component will be VW1 and this component will be VF1. Okay, fine. Now let's say this fluid will enter from somewhere, will exit from somewhere because it is entering from here. So let's say it is exiting from here. Let's say velocity V2. So the components will be, its components will be VW2 and VF2. You can also see it VW2 and VF2 as you know the vector representation. Okay, so now what we are mentioning here, one more thing you can see here, that if you apply this velocity diagram here, then you will only able to see that Vf1 in this direction, that is flow velocity, and a more velocity which is Va1 axial velocity if fluid is at an angle. Okay, so this velocity you will not be able to see in this diagram. Okay, now I will show one more thing. Like if you, I mean, from this figure, you can understand somewhat like this, that this is your entering velocity V1 and that is V1 and this is VW1. So you can think of like this, that this is our rotating machine. It will draw its isometric view. Okay, then you can understand it like this. Fine. So here we can conclude that here let the fluid enter and exit a rotor at section 1 and 2 at radius R1 and R2. At radius R1 and R2. At radius R1 it is entering, and at radius R2 it is exiting. Okay. Under equilibrium condition, when rotor is rotating at a constant angular velocity omega, let's say the rotor is rotating at constant angular velocity omega, then the absolute velocity at the inlet and outlet are resolved into two components, that is VW1 which is world component or tangential component, and the VF, which is the flow or radial component. VF is also called the radial component. So we can say that now if you want to find out the rotor speed, what is the rotor speed? So at the where the fluid is entering at inlet rotor speed, you can find out it as angular velocity into radial distance, and at the outlet u2 will be angular velocity into radial distance. And that how you can find out the torque, you will find out that rate of change of angular momentum means dl by dt, rate of change of angular momentum you can find out. So for that, because here the fluid is flowing, so it is continuously changing, so you don't need to differentiate it, you just find out whatever is the content of the angular momentum. Let's say you will see here that at the inlet of the angular momentum, if you will find, then you will get to know that mass into vw1 into r1, this will be the angular momentum at the inlet. Now because here we are taking the fluid, so mass will be the rate of change and angular momentum will be the rate of change. Okay, so here you don't need to differentiate it. Okay, you just take the you have to just take the difference. Okay, now so actually this is the, what is this, we are taking in the tangential direction, we are taking it as tangential direction, and at the outlet or exit, angular momentum will be m dot vw2 r2. So what is the torque? Torque is the difference of this. So you will find that m dot vw2 r2 minus vw1 r1. So how will you define power? Power is equal to T into omega, you know, this will be m dot vw2 r2 minus vw1 r1 into omega. Fine. Now, if you'll enter this omega inside, then you know from the above figure what is omega r1, omega r2, u1, u2. So we'll get to know that power will be m dot vw2u2 minus vw1 u1. So this is the very important basic equation which is applicable for all turbo machines, and this is called Euler's energy equation. Euler's energy equation. So this equation we can apply in different types of different examples of the turbo machines, like in compressor, in turbines, everywhere. Okay. So now we'll try to understand the velocity diagram, the very most important thing, the velocity diagram. Okay. So first try to understand that how we calculate the relative velocity. Relative velocity is calculated by whatever be the absolute velocity with respect to some other velocity. If we are finding out at 6 and 1, then absolute velocity is 6 and 1 minus with respect to whatever velocity we are finding it, that will be the relative velocity equation. So from this equation, if you want to find out the absolute velocity, then absolute velocity you will get that relative velocity plus the velocity with respect to what you are getting. Okay, so this is the simple vector algebra we'll apply in turbo machines. So let's say we're taking an example. Uh, let's say we have a turbo machine and there is a blade attached here, and it is, let's say it is moving like this. Now, how will you draw the velocity diagram? First, first, uh, let's draw blade different color. Hmm. So first we have to understand how we'll start to draw the velocity diagram. So first of all, what you do that first find out the velocity. This is the angular velocity. It is okay. So whatever be the tangential velocity with respect to this plate, that will be the in this direction only. Tangential direction at inlet or outlet at whatever position will be the this direction only, in the right direction. We have to take the tangential velocity, that is u. Okay, so first at the inlet we want to draw the velocity diagram. So first of all, draw the relative velocity, because the relative velocity is always tangential to the plate. So we'll draw the velocity tangential to plate, it is v, because it is entering, then it will be vr1. Now we know that we have defined that vr is related to V1. VR1 is equal to V1 minus U1. Or we can say that V1 is equal to VR1 plus U1. So we know VR1 and we know the velocity, direction of U. So from that we can find out the direction and the magnitude of the V1. That is absolute velocity. So for that U1, because U1 is moving U1 is moving in this direction, and U1 plus VR1 will be V1. So VR1 we can draw like this, U1 plus VR1 will get V1. This is the inlet velocity diagram. What about the outlet velocity? Outlet velocity we can get like okay. For the outer, same for the outer velocity. First of all, draw the relative velocity VR2 and add U2 in it, because U2 is, I mean, same magnitude. I mean, it depends. If it will be the axial turbo machine, axial flow turbo machine, then the tangential velocity will be same. And it is, if it is circumferential turbo machine, then tangential velocity will be different. And of course, U2, for this case, U2 will be greater than U1, because omega R2 is greater than omega R1, omega omega same, then R2 is greater than R1. Because R2 is greater than R1, that's why U2 is greater than U1. So U2 will be more here. U2 will be more here, and VR1 plus U2 will get V2. So this is the velocity diagram of any kind of turbine machine. Now this will apply in any kind of turbine machine. Fine.